So, today we will be discussing about the analysis of forging, or when you are for the forging analysis, what is the pressure distribution across in an open die forging, and what is the mean pressure, and from that how we can find out the forging load. So, for that this forging analysis will be done. See, let us consider that a case of a plane strain deformation when you are trying to forge a material, open die forging. So, because this part which is shown in this colored region, this is the workpiece material, and it is kept on a bottom die which is stationary, and then through the top die you are applying a pressure and allowing the ram to move downwards. Okay. So, in this way you are allowing the ram to move downwards. So, when as the ram move downwards, when the ram is moving downwards, the height h keeps on changing. Okay. It keeps on decreasing, and here we are assuming that the constant volume relationship is there during plastic deformation when you consider the constant volume relationship. So, as the height keeps on decreasing, there will be a lateral flow of the metal in this direction or perpendicular to a ram movement. So, what will happen is that when this is trying to move towards the side, this leads to the development of frictional force at this interface region. When the metal is trying to move in this direction, there will be frictional force in this. So, at the die workpiece interface region, there will be frictional forces, which is represented. So, we can say that this tau xy is the frictional force which is there. So, this frictional force will be opposing the movement of the lateral direction. So, that means this frictional force will be directed towards the center line. So, that here in this direction it is. So, here also you will find on both the surfaces these frictional forces are coming into picture. So, that surface shear results in frictional force, and the presence of this friction causes an imbalance of forces on the element. This particular, if you take a small element in this, the presence of the friction, you will find that there is an imbalance of force, okay, in the x direction. If you are taking this as the x direction, along the x direction there is an so here we can assume that this is sigma x in this direction and sigma x plus d sigma x in this direction under equilibrium condition. So, you will find there is going to be a difference in the stresses in the element. So, let us assume that the material deforms under plane strain condition. There is no barreling. So, for the time being, for this analysis, let us assume that barreling is not there, and this workpiece is a plate of uniform thickness h. Okay. So, these are our basic assumption. One is plane strain condition. So, material is a plate of uniform thickness, and there is no barreling during the deformation. So, if you take the equilibrium forces on this element along the x direction, then we can write this as sigma x, and if you just take for a unit width which is perpendicular to this plane of this diagram or this screen, if you say unit width is taken, that means width is assumed to be unity, then we can say sigma x into h minus sigma x minus d sigma x into d h into h minus, there are two surfaces are coming. So, 2 tau x y into dx is equal to 0. This is the equilibrium condition of forces in the x direction when you do like that. And if you just do a small mathematical manipulation, and then we can get this equation in this form, that is d sigma x by dx is equal to minus 2 tau x y by h. So, we are getting this relationship. If you consider the von Mises criteria for a plane strain condition, which we have discussed earlier at several instances, that is sigma 1 minus sigma 3 is equal to 2 by root 3 sigma 0, where sigma 0 is the uniaxial yield strength of the material. So, that we can write it in this. This is the notation which you always use it, that okay, here sigma 0 dash. So, and considering this pressure P and sigma x as the positive compressive principal stresses. So, considering P and sigma x as principal stresses, P, we will get that as a sigma 1 is equal to sigma x and sigma 3 is equal to P. If you give that, if you substitute that, we will end up with this relationship, that is sigma 1 minus sigma 3 is equal to sigma 0 dash is equal to P minus sigma x. From this we are getting. Now, if you look at that sigma 0 dash, this is not changing with respect to x. So, if you just take the since it is not changing with this with respect to x, since sigma naught dash is not changing with respect to x. So, we can write it in this form, dP by dx is equal to d sigma x by dx. So, from that, if you substitute in this d sigma by dx in the relationship, so substituting so maybe if I write this as 2 and this as 3, equation 3, substituting into equation 1, we can write it as dP by dx is equal to minus 2 tau xy divided by h. So, we can write it as equation number 4. So, if the shearing stress is related to the normal pressure by Coulomb's law of friction, so that means considering the Coulomb's law of friction, that is tau xy is equal to mu p, where mu is the coefficient of friction and p is the normal pressure which is shown in the figure. The equation number 4 becomes dP by p is equal to minus 2 mu by h into dx. So, we are getting this relationship, it attains this form. So, now if you try to integrate this equation, we will get log p is equal to minus 2 mu x by h plus a constant of integration log c. Okay. So, let us give this as equation number 6. Now, we wanted to find what is the value of c or log c. So, you apply the boundary conditions. So, boundary conditions are see, if you look at the boundary condition at x is equal to a, from the center at x is equal to a, then you will find that sigma x is equal to 0 at the surface, free surface. Okay. So, when the x is equal to a, the sigma x is equal to 0. So, from the von Mises criteria which we wrote it, we can write it as. So, at boundary conditions are at x is equal to a, the lateral stress because it is a free surface, lateral stress at the free surface, that is sigma x is equal to 0. So, from this we get that is sigma 0 dash is equal to p minus sigma x is equal to p, or that is p is equal to sigma 0 dash. and then if you substitute it into equation number 6. So, you can write it as log C is equal to log sigma 0 dash plus 2 mu x by h. So, if you take from this, we can arrive at the equation that P is equal to, in equation number 6, you substitute this. In equation number 6, if you substitute the value of log C, log P is equal to minus 2 mu x by h plus log C, that is log sigma 0 dash plus 2 mu x by h. So, that we can write it as log sigma 0 dash plus 2 mu by h sorry, here it should be 2 mu a by h. So, we can say that 2 mu into a minus x. So, this we can, or from that P is equal to sigma 0 dash into exponential 2 mu by h into a minus x. So, we are getting equation number 7. Now, this equation we can expand it. What is inside the exponential term, we can expand it, because the value of mu is very less. It is always less than 1. Normally, it will be less than 0.5, normal case. So, sometimes it may vary from anywhere from a very low value to, normally for deformation conditions, sliding friction when you are considering, it will come to maximum 0.3 or 0.2. Okay. For analysis purpose, you can use any case, but in normal case it is very less. So, we can write the exponential term, we can expand it. So, since mu is very small, the expansion we can write using e raised to y is equal to 1 plus y squared by 2 factorial plus y cubed by 3 factorial. So, plus infinite term if you go it. So, when you substitute that, we can write it as P is equal to sigma 0 dash into 1 plus 2 mu by h into a minus x. In this form we can write. So, this is the relationship for the variation of pressure on your workpiece with respect to the distance from the center line, where x is the distance from the center line, where x is the distance from the center line. Now, for analysis purpose, it becomes much easier. So, we can also find out what is the pressure distribution, the stress distribution or at the die from the center line. That variation we are getting it, but for calculation purpose, when we wanted to find out the forcing load, it is always a simple method is by calculating the mean forcing pressure and multiplying with this. Otherwise, you will have to keep on integrating from the center to the surface. Okay. But if you are assuming the mean forcing pressure, so this mean forcing pressure can be calculated mean for if you are considering only on one side, forcing pressure P bar. So, that will be 1 by A, because it is from 0 to A, it is varying and we are taking only one side, 0 to A P d x. So, this is small p. So, p dx. So, that if you just write the expansion form, so 1 by a into integral from 0 to a, writing the equation 7. So, if you use the equation 7, so you will find that it is sigma naught exponential 2 mu by h into a minus x. So, it is equal to sigma naught dash into 2 mu by h into a minus x. Sorry, it should be under exponential term, into exponential or e raised to 2 mu by h into a minus x dx. So, that will be like if you just do that sigma naught dash, if you take it outside. So, we can write it as in this form, e raised to 2 mu by h minus 2 mu by h from 0 to a. So, that will be sigma 0 dash by a into e raised to 2 mu by h into 0 by minus 2 mu by h minus e raised to 2 mu by h into a by minus 2 mu by h. Okay. So, that we will get it as p bar is equal to sigma naught dash by a into, if you just do a simplification, you will get it as 1 minus e raised to 2 mu a by h minus 2 mu by h, or that is equal to sigma 0 dash by a into e raised to 2 mu a by h minus 1 by 2 mu by h. So, this is the mean forcing pressure we are getting it for this condition. So, we got the pressure distribution, and if you look at the variation of the pressure distribution, you will find that in this case the equation which we got it as p is equal to sigma naught dash into exponential say 2 mu by h into a minus x. The variation is like this. This is the variation of p. So, at the center you will have a maximum pressure when x is equal to 0. When x is equal to 0, you will have the maximum pressure, and towards the free surface you will find that it is sigma 0, which is the assumption which we have taken also, we are getting it at sigma 0 dash. Okay. So, that is what we are getting it here, and so you will find that it is not a straight line, but in an exponential function it is there, it will be coming down. So, with respect to any distance, radial distance from the center, this is the variation of that. So, now we can also find out that this relationship can also be, say this we can write this in terms of length. So, this, say suppose you take this as L is equal to 2a from that. So, we can also write it as in this form, p is equal to sigma 0 dash into e raised to mu L by h into 1 minus 2 x by L, where L is equal to 2a. So, if you look at this relationship, this particular relation with respect to your L, okay, and h, as L by h increases, the resistance to compressive forces deformations of P, it increases rapidly. So, this point is used as an advantage in impression die forging. So, there we have already discussed that when the die is closing, as the die closes, the flash is formed. And now, once the flash starts forming, you will find that in that curve which we found the stress keeps on increasing, that is, if this is the stroke and this is the force. So, we found like this. So, once this is the point where the flash starts forming and the pressure required for the deformation keeps on increasing. And when the thickness, say with L by H, if H is very small compared to the L, then you will find that okay, your forces are going to increase like anything. So, with the thickness of the slash decreasing, the forces necessary will be, or the stresses necessary for the deformation will be very high. That is why you will find that it is much more safer, because the metal to deform and form the flash and then fall into the flash gutter, the pressure will be higher. That means, whatever force you are applying, that will be completely used inside the die cavity, and then it will be so high inside the die cavity, the pressure or stresses will be very high. So, that complete filling of the die cavity take place, and still when the pressure increases, okay, this flash, through the flash, now it will skirt out and then fall into the flash gutter. So, that is one. So, that way the formation of the flash is very important, and as the flash thickness decreases, the pressure buildup will be very high for the resistance to deformation will be very, very high in the flash, but that high stresses will be transmitted into the workpiece material inside the die cavity. Now, this case we were considering only we were considering a case of sliding friction, okay, where the Coulomb's law of friction was applicable, or the metal, we assume that the metal is just sliding. So, because of the lateral force, though there is a frictional force which is coming, the metal keeps on sliding and moving, and at the interface there is a relative motion. But in almost all the cases of forging, this may not be true. Okay. So, because if you look at the center, the pressure is very high, but it is coming down. So, there will be every chance that there is a sticking which is coming, it will be sticking to the die. This effect of sticking and sliding friction we have discussed in our effect of friction earlier lecture. So, let us do the analysis considering sticking friction. So, the interface shear, so only thing our initial equation which we came across was 2, let us say, sticking friction. Our differential equation which we found was dP by dx is equal to minus 2 tau xy by h. This is what our equation number 4 we have written that. Now, for sticking friction, the interface shear stress with a friction factor m. So, we can write it that tau xy, which is the shear stress at the interface. So, that is tau I, we can write it as m k, where m is the friction factor. And you know that for perfect sticking, m is equal to 1, for perfect sliding, m is equal to 0, that is what our basic assumption we have taken. So, from this if you assume that tau xy is equal to m k, if you substitute it into this equation, you will find that dP by dx is equal to minus 2 m k by h. So, from this we can arrive at dP is equal to 2 m k by h into dx, and we know that the value of k is equal to. So, from that and sigma naught, so that we can just write that that is dP by dx. So, we can write it as is equal to, substituting for 2 k, we can say that 2 sigma 0 by root 3 into m into dx by h. So, that also is equal to we can write the, so here minus is there, minus sigma 0 dash into m into dx by h we are getting. So, now integrating this becomes very simple, straightforward. We will get it as p is equal to, so we can remove this. Okay. P is equal to minus sigma naught m into x by h plus c, because it is a straight line equation, that is why we are taking c. But earlier also we found that p is equal to sigma naught, we got it the same at x is equal to a. So, from that, that is if you, this is the boundary condition, that is from that we can write it as c is equal to sigma naught plus sigma naught into m into a x by h into a by h. So, if you substitute that in this equation, so we will write that is p is equal to minus sigma naught dash into m into x by h plus sigma naught dash plus sigma naught dash into m into a by h. So, that is p, you will get it as sigma naught dash plus sigma naught dash into m by h into a minus x. So, we will get this as equation number 11. This pressure distribution is linear with respect to the with the distance from the center line. See, it will be like this. This is the it is linear. So, from the center line you will find that, because the equation is that see, if you look at it, p is equal to sigma naught dash into m by h into a minus x plus sigma 0 dash. So, this is so at this x is equal to a, you are getting it this is 0 and you will get it as sigma 0 dash here. Okay. And then at x is equal to 0, you will get the maximum value p max. Okay. So, that is what we are getting it. So, when that so that means there is a limit. So, since the pressure distribution here is linear, we can see that in actual case the there will be, it will neither be perfectly sliding. So, if it is perfect sliding, then m is equal to 0, and where Coulomb's law of friction will be applicable. And if it is perfectly sticking, m is equal to 1, then we can get this relationship with m is equal to 1, we can get the value, okay, for perfect sticking condition. But in actual case, it will be an intermediate between up to some distance from the center. See, if you calculate the value of P max for using sliding friction and sticking friction, then you will find that it is like this. Okay, a relationship will be there. So, from the center to some distance, if you just take some distance here, from the center up to some distance, you will find that the stress resistance is less here. So, the moment the stress reaches here, it will start deforming. So, that means in this condition, it is the sticking friction which will be prevailing from the center to some distance. Now, beyond that, you will find that the lower stress is for the sliding friction. So, when the stress reaches there, metal will start sliding from that area. So, that sliding of the metal will take place. So, in actual case, in real application, when the deformation is there, from the center to some distance there is. So, this part it is you can say sticking condition, and here it is sliding condition. So, when that, so there is a limit up to which with the sliding friction can exist at the die workpiece surface. So, when that limit is reached, the interfacial shear of the workpiece occurs at a value of the flow stress which is equal to tau I is equal to k. So, that means tau I is equal to k, where k is equal to sigma 0 by root 3. So, in general we can write that tau I is equal to m k. So, that we can say tau x y, not tau I, so which is at the interface, tau x y is equal to k is equal to sigma 0 by root 3 is equal to sigma 0 by 2 when you look at it. And if the distance from the center line is if you just consider this is x 1, so that where these two are equal. So, in that case we can write that tau x y at x is equal to x 1 is equal to mu p is equal to k is equal to sigma 0 dash by 2. So, that means p is equal to sigma 0 dash by 2 mu. Now, if you use this for the sliding condition, that is p is equal to sigma 0 dash by 2 mu, the sliding condition if you write it as which is sigma 0 dash into exponential say 2 mu by h into a minus x 1 at x is equal to x 1 is what we are considering. So, from this will get cancelled. So, we can write it as say log 1 by 2 mu is equal to 2 mu by h into a minus x 1. So, that means we can write it as h is equal to h by 2 mu into log one by 2 mu is equal to a minus x 1. So, therefore, x 1 is equal to a minus h by 2 mu into log 1 by 2 mu. So, that way we can find out this the distance x 1 at which the transition from sticking to sliding conditions exist. Okay. So, that is one method of finding out actually. Now, we can also just look at certain condition. So, in the sticking friction when you look at it, so we can also find out what is the pressure. So, actual pressure should be like you have to integrate between from x is equal to 0 to x is equal to x 1 considering the sticking friction and the pressure distribution, and from this x is equal to x 1 to x is equal to a for the sliding condition. So, we have to find out this how to determine this. We know the pressure distribution, but we can also find out the like for special case of sticking friction. So, for perfect sticking condition now m is equal to 1 for perfect sticking condition for m is equal to 1, and so we will get it as p is equal to sigma naught dash into a minus x by h plus 1. We can write this equation, and the mean pressure p bar is equal to 1 by a into integral p dx, that is equal to 1 by a into 0 to a. Sigma 0 dash into a minus x by h plus 1. So, that is equal to sigma naught dash by a into say a x. So, a into h we can write a x minus x squared by 2 plus a h into 0 to a. So, that is p bar is equal to sigma naught dash into a by 2 h plus 1. We can get this. and you can just integrate from here to here using the mean stress, and then from here to here you can integrate using the earlier equation, this equation for this, and then find out the sum of all those things. So, that is what we can always get it. Now, the thing is that once you get this, you have to multiply width of the specimen, so that you get the total load. This is what we are calculating was for unit width. So, you have to multiply with the total width of the width of your workpiece, and then find out that the total load which is required for this forging. So, open die forging. The same thing we can also do it for the same relationship can be used for the deformation of the flash, that also. So, you can always calculate. So, you will find that when the thickness comes, when the thickness is very less, the pressure total force required for, or the pressure required for the deformation increases very high. That is why towards the end, when the flash thickness keeps on decreasing less, the pressure will be very high. Okay. Thank you.